Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the principle of corresponding states. We have said that gases follow the ideal gas equation closely at low pressures and high temperatures. But what exactly constitutes low pressure or high temperature? Is minus 100 degrees centigrade a low temperature? It definitely is for most substances, but not for air. Air or nitrogen can be treated as an ideal gas at this temperature and atmospheric pressure with an error under 1%. This is because nitrogen is well over its critical temperature and away from the saturation region. At this temperature and pressure, however, most substances would exist in the solid phase. Therefore, the pressure or temperature of a substance is high or low relative to its critical temperature or pressure. Gases deviate from the ideal gas behavior the most in the neighborhood of the critical point. Gases behave differently at a given temperature and pressure, but they behave very much the same at temperatures and pressures normalized with respect to their critical temperatures and pressures. The normalization is done as here PR is called the reduced pressure and TR the reduced temperature. The Z factor for all gases is approximately the same at the same reduced pressure and temperature. This is called the principle of corresponding states. The equation of corresponding state is any equation of state expressed by dimensional properties can be expressed as an equation of corresponding state by dimensionless properties, such as the van der Waals equation. From the previous derivations we have, substitute B into A and divided by PC, VC yields. This is the van der Waals corresponding state equation. The compressibility factor can also be used to express the van der Waals corresponding state equation. By definition of the compressibility factor, we have expression of VR. Substitute VR into equation 572 yields equation 575. Equation 572 and 575 are both van der Waals equation of corresponding state. The formula does not contain constants that reflect the characteristics of different substances, and it is universal. It is applicable to any van der Waals gas. However, if the Waals equation of corresponding state is used for any other real gas, the error will be large, since the critical compressibility factor of the actual gas is much less than 3/8. Although the van der Waals equation of corresponding state is not suitable for the quantitative calculation of real gases, it provides a revelation. All van der Waals gases can use an expression containing 3 reduced parameters. Then, for all the van der Waals gases, as long as 2 reduced parameters are the same, the third one must be the same. All the van der Waals gases are thermodynamically similar. They have the same thermodynamic surface in the 3-dimensional diagram, and any point on the thermodynamic surface represents a corresponding state of all the van der Waals gases. A general corollary, then, is, for the thermodynamically similar fluids, if 2 of the 3 parameters are the same, then the third must be the same. This is the corresponding state principle. Thermodynamically similar fluids with the same reduced parameters are in the same corresponding state. Okay, that's all for this task. Thank you very much, and see you next time.